All right, so in this lecture, we're going to learn about thermodynamics systems. So this is going to be mostly covering first law of thermodynamics that relates internal energy of the system to the amount of work done and heat added, because work done and heat added are two mechanisms of energy transfer. And every time there's a energy transfer, then we can see that it's, you can use that to calculate the amount of internal energy changed in the system. And general thermodynamic system represent um, examples where the system can exchange energy with surroundings, and this energy can be done on the system, or even the system itself can do work. For example, in this case, the system, which are popcorn, does work in opening the lid of the pot. So we're going to be considering, several examples like this. All right. So first, let's look at what we mean by thermodynamic system. So let's say you have a system that is open to environment. That means it's not a closed system, so the energy can be transferred into the system and energy can be transferred out of the system. And now again, we have two mechanisms of energy transfer. One is work done, the other one is heat added. Okay. Now, you can see over here it says careful of signs. And this is important because we learned that if the work done is positive, energy is transferred into the system. And if the work done is negative, energy is transferred out of the system. Now, one of the things we're going to also add to that is the work done by the system compared to the work done on the system. So, for example, you can see that it says work done is positive when it is done by the system and negative when it is done on the system. That means if the work is done by the system, so for example, when the popcorn is, you know, doing work and, raising the lid, that's a work done by the system. Okay. When you take a piston and, push it down and compressing, let's say, the volume, that's a work done on the system. So we have to be kind of like careful with that. And we also know about the Q, which is the heat, and we know that Q is generally positive when energy transfers into the system and temperature, let's say, increases, and Q is negative when when the energy is removed and temperature decreases. Remember, the Q is heat, energy transfer due to the change in temperature, and work done is a mechanical work done that generally works in terms of, there's some kind of push or pull. So again, what we do here is work can be done on the system and can be done by the system, and work is when it's done by the system, it's positive for expansion. Okay, so that's why what we have here is this. Again, work is done, you know by the system, take to be positive, and work is done on the system, take to be negative. So that's one of the important things to know about the first law of thermodynamics. Okay. So now, um, internal energy of the ideal gas. So as I mentioned, right, we're going to relate work done and heat added to the internal energy of the of the ideal gas. And the internal energy depends only on the temperature. Okay, it doesn't depend on the pressure or volume, because pressure and volume, remember, those are other macroscopic quantities that describe your system, and internal energy only depends on one microscopic quantity, and that's the temperature. Because we learned in the previous lecture that you know um, internal energy is proportional to the temperature of the system. So whenever we're considering, um, let's say, free expansion, the temperature of an ideal gas does not change, and the equation for the internal energy, the one that proportional to the temperature, can be written as energy is equals to 3 halves nRT. Remember, we had previously written energy in terms of kinetic energy, but remember, that's the kinetic energy of the particles within our system. So the internal energy is basically the energy that we can think of, like, let's say, whenever they're colliding, their potential kinetic energy converted to the internal energy. So that internal energy is always, technically only depends on the temperature from, all the other variables of the state. All right. So, in terms of then the work done, there are several equations for the work done depending what type of processes we have. So, we're going to talk about all of those. So, we can see that we can understand the work done by gas in a volume change by considering molecule in the gas. So, for example, you have a container where you have some kind of, um, a fluid right inside inside, and there is a movable piston. So the idea here is that those molecules moving around constantly, and apart from colliding with the wall, they also collide with the piston. And whenever they collide with the piston, they exert force, right? So they exert force, and that force eventually, allows, pushes the piston, right? So the piston moves away from the molecule during the collision because, there's a force. So there's a force acting from those molecules, right? So whenever then those molecules collide with the piston, they exert force, and then you can see, right, then let's say the piston moves, from here to there. So there's a then delta x. So whenever the volume increases, so whenever the volume of the gas increases, the molecule does positive work. Okay, but whenever the volume decreases, then you can say that molecule does negative work. Okay, so then work is negative if the volume decreases. So now, using that, we can set up an equation for the work done. So you can see, right, in terms of when there is a change in volume, so then the work done equals V2 minus V1. Right. So again, when let's say the volume decreases, when volume decreases, then this quantity you can see, right, is negative because V2 is smaller than V1. So then, this equation for the work done is then P times delta V, right? So it's P times delta V, where it's changing volume. So when the volume decreases, work done is negative. When the volume is increases, work done is positive. So those are the one of the things that you have to be careful in terms of positive, negative sign of for the work done. All right. So in this diagram, which is a PV diagram, so you take the pressure to be on the y-axis and the volume on the x-axis, and represent this in terms of the change in your state. So let's say one represent your state, your initial state, you can say, so which is given in terms of pressure one and volume one, and also let's say temperature one. We're going to see that how we can kind of incorporate temperature into these PV diagrams. So in this case, let's say if your state changes, let's say it goes from state one to state two. That means, for example, you can see, right, two represents then your state two. So you can see, right, then there's a change in pressure and change in volume. So one of the things we can see here is the volume increased as you go from state one to state two. That means, volume is increased. That means the work was done uh, by the molecules, right? It's a positive work done by the molecules to increase the volume. And, in the process, then we have then the pressure decrease. Okay. So there, another way we can find the work done is by calculating the area under the graph. So the work done is equals to the area, and here work done is positive. So all we have to do is just basically find the area under the graph, and that's exactly, equal to the work done. All right, so work done, um, that means, you have an equation that you can use to calculate. Also, in a way, there's another method doing the PV diagram, find the work done by finding the area under the graph. All right, so in this graph, right, so what you have here is you have an expansion with varying pressure. That means when the pressure changes, that means when the pressure decreases, then the volume increases, because one of the things we know here is that pressure is direct, inversely proportional to the volume. We know that when the volume is increasing, the pressure decreases. Okay. And whenever there is a compression, which actually, this graph doesn't represent. So if you have a PV diagram, so if let's say you have a compression, for example, something like this, and the arrow indicates in which direction you're moving. So let's say this is 1 and this is 2. So then you can see, right, this is being volume 1, this is being volume 2, which is basically you are increasing your pressure as the volume basically decreases. So the volume 2 is now less than volume 1, and then it goes into, you know, changing the pressure as well. So pressure increases when the volume decreases. Again, this is, you know, let's say work done is negative in this case, because again, when the volume decreases, the work done is negative. But one of the things we're going to see is that not every time when the volume decreases, pressure necessarily changes. So this particular graph represents, you know, a compression with varying pressure. There are also, you know, examples of the compression where the pressure actually remains the same. But obviously, you know, one of the things we're going to see here is that, you know, assuming in this particular case, the temperature, for example, doesn't change. So for this case, temperature doesn't change when we go from state 1 to state 2, but it's possible that we we will have a system where when the volume changes, remember, when the volume changes, pressure changes. When the temperature changes, pressure also changes. That means it's possible to um, have a system where you are decreasing the volume, which increases pressure, but also you are decreasing the temperature, which decreases the pressure. And it can be done such that amount of the pressure that would increase due to the decreasing volume can be compensated by, you know, let's say decrease in pressure when you decrease the temperature. That means, you know, pressure increases when volume decreases, for example, right now. But then if you also decrease the temperature, then pressure also decreases and they can cancel each other and you can have a constant pressure. All right, so that type of process is can be achieved by, you know, by again combining those two, you know, system variables together, right? That means, you know, volume and temperature change together in order to keep the pressure constant, because we know that pressure is inversely proportional to the volume, but then directly proportional to temperature, right? So, for example, look at this, you know, this particular diagram, PV diagram. Here's, you know, state 1. In this case, I have pressure and I have volume for state 1. But then clearly I am changing the volume. I'm increasing the volume. That means, you know, work done is positive, right? And according to this equation, when I'm increasing the volume, pressure should decrease, but it doesn't. It remains constant, which means that at the same time, something else happening. So as the volume, you know, increases, for example, volume doubles, well, exactly same time we can double the temperature, and that effect can cancel each other and you have the same pressure as before. That's why when you go to state 2, even though your volume doubled, which clearly can be seen in this diagram, temperature is also doubled, which actually cannot be seen in diagram, but we will see there is a way to incorporate this, you know, temperature in this PV diagram as well. Okay, so that's one of the things we're going to see in just a little bit. All right. So, but again, in this case, what we have here is the work done is equals to pressure times change in volume. That means for this particular, you know, process, this is known a process where the pressure remains constant. You know, the volume increases, right, and the work done is positive. All right. So now, what we can do here is we can look at in terms of work work done by, you know, by changing some of the, you know, states of our system. So for example, we have state 1, okay, and then there's 2 and there's 3 and there's 4. And one of the things we can see is that work done depends on the path chosen. Okay, so for example, consider 3 different paths on a PV diagram for getting from state 1 to state 2. All right, so that means our goal is to go from state 1 to state 2. You can see, right, there are 3 different paths. I can go to state 1 taking this path. I can go to state 2, from state 1 to state 2. I can go to state 2 taking, from state 1 to state 4 first, and then from state 4 to state 2. That means taking basically this path. Or we can go from state 1 to state 3. That means basically keeping the pressure constant and increasing the volume, and then from here keeping the volume constant and decreasing the pressure. That means, exactly opposite. For this one, it was, keeping the volume constant, decreasing pressure, and then keeping the pressure constant and increasing the volume. Now, the question that, are they all the same? Is the, work done the same for all of those paths? Well, as you can see from the title, right, of this slide, the work does depend on the path chosen. That means every single path gives me different, a different amount of work done. Okay, so let's look at, let's say, going 1, 3, and 2. Well, 1, 3, and 2 is actually does the largest amount of work. Why? Because remember, the work done is the area under the graph. And now this is the area under this graph, which is basically the amount of work done represent all that area. Okay, so then if I go to 1, 4, and 2, then only this is the amount of work done, which is clearly a whole lot less than, let's say, in the previous slide, when you go 1, 3, and 2. Okay, and then obviously then going from 1 to 2, it's kind of like the middle in terms of the work done, right? So the somewhere between, maximum work done and a minimum work done. So let's say this is, still you do amount of work done, which is, greater than going 1, 4, and 2, but less than going 1, 3, and 2. Again, in a way, sometimes depend on which path is best, right? So you might see, like, let's say, us incorporating, different paths depending what needed to be achieved. So in this case, if you want to go from 1 to 2 with the least amount of work, you go 1, 4, and 2. With most amount of work, you go 1, 3, and 2. So then again, that depends basically on whatever needed. All right. So I've been saying that, we're going to be able to incorporate the temperature into our diagrams, and that's what we have. So on the left side, you can see that this PV diagram, and the blue lines actually represent temperature. So, okay, so the vertical line is the pressure, horizontal line is the volume, and blue lines then are the temperature. So the temperature actually, constant along that blue line. So for example, I'm going to take this one over here. So that means this line has the same constant temperature. Okay. So then the second line has also constant temperature, but let's say this, let's call this T2, this is T1. Okay. So then T1 is actually lower temperature than T2 because closer the line to the origin, lower the temperature. Further away from the origin, greater the temperature. So these are known as isotherms, or, basically isotherm is the lines, and isothermal means that you are along the line that doesn't, change the temperature. So for example, let's look at, you are here at A. Okay. That means A is our starting, let's say state. Okay. Now, if we go from A to state 1, you can see, right, I go from one isotherm to another isotherm. That means I go down one isotherm. Okay. So going down one isotherm means that I am decreasing temperature. Okay. I'm decreasing my temperature. Okay. So if I go from A to 2, again, I'm decreasing my temperature. But there's a difference in terms of how I decrease my temperature. So one of the things we're going to see is that every one of those lines actually represents very specific type of process. And you can see the name for those. For example, if you go from A to 1, it is known as an adiabatic. Okay, and we're going to talk about adiabatic, but this is adiabatic where you do decrease your temperature. You always decrease your temperature when you have adiabatic, or you can say you always change your temperature. And you not only change your temperature, but you can see, right, going from A to 1, you also change your volume and you also change your pressure. So all of those things are changed if you go from A to 1. So that state is adiabatic, where volume, pressure, and temperature are changed. Let's look at from A to 2. This you can see, right? It's a vertical line. Going from A to 2, it's a vertical line. And this particular process, you can see that pressure decreases, temperature decreases, but volume remains constant. This is known as an isochoric. Okay, so you are decreasing the temperature because you can see, right? Temperature at point 2 is less than temperature at point A. So we're decreasing the temperature, we're decreasing the pressure, but volume remains constant. This is known as the isochoric process, constant volume process. Going from A to 3 is then temperature increases, so T3 is greater than TA, volume increases, right? But pressure remains constant. So this is known as the isobaric process, constant pressure process. So in this particular case, we are increasing temperature, or things like this. You can also go from 3 to A, right? The idea is that you're changing temperature, you're changing volume, but pressure remains constant. This is one of those things when I say, right, if you increase the volume, right? If you increase the volume, pressure decreases. But increasing temperature then increases pressure, and they compensate for one another, and the pressure remains constant. All right, so the last one going from A to 4. And you can see, right, A to 4 is on the same blue line. That means same isotherm. This is known as the isothermal process. Isothermal process changes pressure, changes volume, but remains, keeps the temperature constant. T4 and TA are along the same isotherm, so they temperature have this, they have the same temperature. All right, so again, so isotherms are basically those blue lines, and closer they are to the origin, right? So lower the temperature, further you are, increases the temperature. Okay. So again, now we have those two diagrams on the right of that. So you have um, two processes. One is, again, you can see, right, changing volume, pressure remains constant. So what type of process is that? It should be isobaric process. Okay, isobaric process is a constant pressure, but in this particular case we are decreasing the volume. Well, if you're decreasing the volume, work done is negative, remember? And how can we then keep the pressure constant? Well, remember, so this is one isotherm, this is another isotherm, so we are decreasing temperature. That's why when we decrease the volume, pressure increases, but decreasing temperature, increases pressure, and they compensate for one another. Okay. Well, actually, decreasing the volume increases pressure, decreasing the temperature decreases the pressure, and the proportion, they do that proportionally, so pressure remains constant. And here's another example where the increase in pressure achieved by the decrease in volume. And in this particular case, there's a varying pressure, and you can see, right, it is more or less along the same isotherm. So then the temperature state 1 and 2 are exactly the same. So temperature remains constant, but pressure is increased because of the decrease in volume. All right, so this is what we have for the isotherms. So the isotherms is when you go from one state to another state along those, isotherms, which are the constant temperature lines. And the work done as you go along those isotherms is given in terms of nRT, which is number of moles times the gas constant times the temperature, because it's the same for the initial and final, then times ln of V2 over V1. Because one thing we're doing, we are changing the volume, right? We are changing the volume. And then the work done is basically given in terms of this equation. All right. So for this particular process, here's the equation for the work done. So you have to be careful in terms of, if you know that your process is an isotherm or isothermal process, that's the equation for the work done. Okay. Not P times delta V. P times delta V is for the, because, right, it's isobaric process. So here you can do P times delta V. For this process, which is isochoric, there is no change in volume, which means there is no work done. So the pressure times delta V, since there is no change in volume, the work done then is 0. That means there is no work done going from A to 2. There is a work done going from A to 3. There is a work done going from A to 1, and there's a work done going from 8 to 4. Okay, so then we're gonna have to be able to calculate all of those, of different amount of work done. Okay, so this is again work done equation for the isothermal process. All right, so let's look at an example here. So we're going to consider that loop that we looked at already. So it's a closed loop going to 1 to 3 to 2 to 4 to 1. That means this time we're going to go like this: 1 3 2 4 1. So going in this particular direction. Okay. So this is a cyclic process in which the initial and final states are the same. So we're going to find the total work done by the system in this cyclic process and show that it is equal to the area enclosed by the loop. Okay. Now, if we are going, 1 to 3 to 2 to 4 to 1, there is amount of work done. So the work done is not zero. So, and we're going to be able to find based on this particular path. Okay. So we're going to find, that, and then part B says, how is the work done for the process related to the work done if the loop is traversed in the opposite direction? All right. So let's then look at in terms of how we can calculate the work done, going through this, cycle. All right. So going from 1 to 3. So 1, 2, 3. So one of the things we can say, okay, work done going from 1 to 3 is equals to, and you can see, right, it's an isobaric process. That means the pressure remains constant and you have the, a volume expansion. So it's equals to pressure times delta V. So which will be pressure 1 times then V2 minus V1. Okay, so that's, work done by for that. Then we go from 3 to 2. So for this one, work done from 3 to 2 is, if you write this equation, right, P times delta V, you can see, right, there is no change in volume, so there is no work done. So the work done going from 3 to 2, which is, isochoric process, right, doesn't change the volume, right? Uh, that means volume is constant, so then there is no work done. Then we go from 2 to 4. Okay, so then going from 2 to 4, then work done 2 to 4 is equals to pressure 2 that times v1 minus v2. And going then 4 to 1, then work done is equals to, again, 0 because there is no change in volume. Okay, then the total work done is equals to work done 1 to 3 plus work done 3 to 2. This is 3 to 2 plus work done 2 to 4, and then plus work done from 4 to 1. So then this is equals to 0. uh, P1 times V1, V2 minus V1, then plus 0, right? For the, that means, this is 0 and this is 0. Then it's just basically plus P2, then V1 minus V2. Okay. Which at the end up being V net is equals to, if, let's say you write those down, and we end up with P1 minus P2 times V2 minus V1. And this is basically nothing but the area under the, PV plane. Okay, so this is basically the area under the PV plane. Okay. All right, so let's call this, A. Now, in terms of what happens when, we reverse the order, right? Go from 1 to 4 to 2 and to 3 and then to 1. Well, in this case, we basically have the pressures that are going to be the same. So you're going to get same equation. The pressures are the same. It just then the volume, right, switch. So then in a way, you're going to get exactly same work done, but, it is just a negative. That means, work done for the 1, 4, 2, 3, 1 is equal to the negative of work done by going from, 1 3, 2, 4, 1. So and that's going to be then the answer for that. Which this was the answer for the first one. All right. Now the next here is first law of thermodynamics. So the first law of thermodynamics says the change in internal energy U of a system is equal to the heat added minus the work done by the system. Okay. So in this particular equation, Q is the heat added due to the change in temperature, and the work done is the mechanical work done on this, by the system. Okay. Remember, work done is positive, right? When you have a volume expansion, and negative when you have a compression. So the first law of thermodynamics is just a generalization of the conservation of energy. Both Q and W depend on the path chosen between states, but delta U is independent of the path. Because remember, delta U just depends on the temperature only. All right. So here's an example. So we have, in a thermodynamics process, the internal energy of a system may increase. So, for example, the 150 joules is added to the system by a form of heat. Then the system did 100 joules of work. So that means the system gained 150 joules but lost 100 joules. So when we calculate change in thermal energy, it's 150 minus 100, so we get plus 50 joules. That means that's the amount of energy net, right? Amount of energy for the uh, internal energy. It can also decrease. So, for example, uh, there's a work done on the system, which basically W equals negative 100 joules, um, which means that, for example, this is the energy goes into the system because of the external, forces doing work, and but also then 150 joules of heat energy was removed. Okay, so 150 joules of heat energy was removed. So then delta equals Q, which is negative 150 joules, minus the work done, which is negative because work done is on the system. So this means that work done is on the system, and then that basically negative 150 minus 100 give us negative 50 joules. That means even though 100 joules was added to the system by the external forces, 150 joules was lost because of the temperature difference, probably so. And then internal energy of the system was lost. So there's now less internal energy than it was before. Again, what will this mean in terms of, let's say, for example, temperature of the system? Well, if you lose internal energy, your temperature will decrease because internal energy is directly proportional to the temperature. You lose internal energy, you decrease your temperature. You gain internal energy, you increase your system temperature. Okay. So, and there are some processes where the internal energy may remain the same. So in a system shown below, the heat added to the system equals the work done by the system. So the internal energy of the system is unchanged. This generally happens when you have an isothermal system, isothermal process. Remember, isothermal process, you have exactly same temperature. Well, if your temperature doesn't change, your internal energy doesn't change, which means that, let's say, same amount of energy was transferred into the system and out of the system. Doesn't mean that there was no, let's say, Q or W. They're just basically same amount, and when you subtract, then you get basically zero. That means, for example, here 150 joules was added to the system, but then system did 150 joules of work, which was, that means energy gone from the system. So then internal energy did not change. Again, this is usually happens when you have an isothermal process. All right. So now there are four specific kinds of thermodynamics processes, which most of them we already seen. So we have seen isochoric, which is the volume remains constant, so work done is zero. We saw isobaric, where the pressure remains constant, so the work done is P times change in volume. And we saw isothermal, where the temperature remains constant. Okay, remember, so the work done for this particular process is nRT, right? Then ln V2 over V1. So this is very specific type of process where the work done is basically given with this equation. So you have to, be careful in terms of if you're using this equation or not. All right, so then let's look at in terms of adiabatic process. So adiabatic process is, remember, that specific type of process where you have, let's say you have a PV diagram. So let me draw the, isotherms. So let's say these are isotherms. Okay. Now, for example, let me do some of the, like, isochoric. Isochoric will mean that, let's say you're here, state one, and you go to here, state two. So you're like a straight, you know, down like this, where volume doesn't change. So there's no work done. Okay. So isobaric process, again, will be an example of, all right, so I'll just do it like this. Example, going from 1 to 2 like this. So your pressure remains constant, but then your volume changes from V1 to V2. Okay, and the work done can be calculated like that. All right. So isothermal process, then when these are your isotherms, and you go from, let's say, state one to state two along the same isotherm. Okay, so they can say, right, there's a change in volume, change in pressure, but no change in temperature. So technically, then same amount of work done as the energy added or removed, right, is achieved. So internal energy doesn't change. Adiabatic is basically is when there's no heat added. Okay, and the internal energy basically equals to the negative of the work done, because delta U equals Q minus work done. This is zero, so it's equal to the negative of work done. And for the ice, let's say for this particular process, what happens? So let's say this is my isotherms. So you go from one to, let's say, two over here. So you go like this. Okay. That means there is change in temperature, there is change in pressure, there is change in volume, right? And all of those three things change, but there is no heat added. Generally, it happens when something is done really fast. So then energy as a heat, right, doesn't have time to escape. Okay, so usually it happens, kind of like a quick processes. All right, so here's an example of that. So adiabatic process is when, for example, the cork is popped on a bottle of champagne. The pressurized gases inside the bottle expand rapidly and do positive work on the outside air. There's little time for the gases to exchange heat with their surroundings, so the expansion is nearly adiabatic. Hence, the internal energy of the expanding gases decreases because it's equal to the negative of the work done, and their temperature drops. Okay, again, why is the internal energy decrease? Because system loses energy, right? Or transfers energy out of the system by doing positive work. Remember, here you have to think like this: when the gases do positive work, energy is removed from the system. That means that's why internal energy then decreases and the temperature drops. Okay, so whenever internal energy decreases, temperature drops. All right, so this makes water vapor condense and form a miniature cloud, like you can see over there. That usually happens when you open the champagne. All right, so let's look at then isobaric process. You can see, right, most cooking involves isobaric processes. That's because the air pressure above a saucepan or frying pan or inside a microwave oven remains essentially constant while food is being heated. Okay, so this is basically isobaric process, which means constant pressure. Okay, so we can see an example here involving some of those processes again. So we have a gas that undergoes two processes. In the first, the volume remains constant at zero point 0.2 cubic meters, and the pressure increases from 2 times 10 to the 5 Pascal to 5 times 10 to the 5 Pascal. Okay. Um, I guess there's a period there. So let's see what we have. The second process is a compression to a volume of 0.12 cubic meter at the constant pressure of 5 times 10 to the 5 Pascal. Okay, so we're gonna then in a PV diagram show both of those processes. Okay, so think like this. First, constant volume, increasing pressure. Remember, that's basically an isochoric process, right? Constant volume, increasing pressure. That means the vertical line. But we are increasing the pressure, so it's a vertically moving upward. And then while keeping the pressure constant, we are decreasing the volume. That means it's a horizontal going to the left. And that's the diagram for that. That means we start from 1, which is zero point 0.2 cubic meters. Then we keep the volume constant, then go to the stage 2, which is increasing the pressure. Then we move, we have an isobaric process where the pressure is constant, then we decrease the volume to zero point 0.2. All right, so this is basically the PV diagram for that. Okay. Next, we want to find the total work done by the gas during both processes. All right, so um, if we go back here, we can see that finding the work done, let's say first work done going from 1 to 2. Well, we know that this is 0, right? It's an isochoric process. For isochoric process, work done is 0. Then going from 2 to 3, what I have here is just P times delta V. Okay. Pressure remains constant and volume changes. So this one is isobaric process. Okay. And then we can calculate the work done going from 2 to 3. So pressure, which is 5 times 10 to the 5 Pascal, then times volume change, which is 0.12 cubic meters, which is the final, minus zero point 0.2 cubic meters, which is the initial. Okay. So then we're going to get negative 4 times 10 to the 4 joules. Okay. And it's negative because we are, doing work on the system. Okay. So the volume decreases. Okay. That means if we calculate the total work done, so isochoric process is 0 work done, and isobaric process negative 4 times 10 to the 4. So the total is negative 4 times 10 to the 4 joules. All right. So that's for this example. That means we needed to do the PV diagram and then calculate the work done. Let's look at another example here. So the process ABC shown in the PV diagram involves 0.0175 mole of an ideal gas. What was the lowest temperature the gas reached in this process, and where did it occur? How much work was done by or on the gas from A to B and from B to C? And if 215 joules of heat was put into the gas during ABC, right, the process, how many of, so let me see. All right, we fix this. So how many of those joules went into internal energy? All right, so let's look at then this example. So we're given PV diagram in terms of some of the values for A, B, and C, right? Pressure and volume and things like that. And we want to, and also we're given number of moles, right? So, and we want to find what was the lowest temperature of the gas reached in this process. So in terms of then temperature, remember temperature, you have to look at from in terms of, let's say, those isotherms. So the isotherms kind of go like this, right? So there's going to be, let's say, an isotherm like this, an isotherm like that, and isotherms like this. So in terms of, let's say, the isotherms for point A, B, and C, let's say which temperature will be the lowest. Well, the isotherm that is closest to the origin, remember. That means here at point A, you're going to get the lowest temperature, okay? And you can technically even calculate because you have a pressure, volume, number of moles. You can plug it into the PV diagram, ideal gas law equation, and then calculate it. But that's that, in terms of temperature A is the, less than temperature at B and less than temperature at C. So, and we should be able to even, calculate that by, using those values. Again, hopefully you guys can see that from the graph, and then we can use this, equation to calculate, because what I have here is this. PV equals nRT. And then this is then P at A, V at A, and T at A. And number of moles doesn't change for, going from A, B, C, and things like that. Then I can rearrange and solve for TA, which will be then PA VA over N times R. All right. So pressure at A is 0.2 Pascal. So 0.2 ATM. 0.2 ATM, where then we can say 1 ATM is 1.013 times 10 to the Pascal. And then volume is 2 liters, which then becomes 2 times 10 to the negative 3, cubic meters by converting into cubic meters. And then N here is 0.0175 moles. And then R here is 8.315 joules per mole Kelvin. All right, so plugging everything, calculating temperature, we get 278 Kelvin. That's the lowest temperature. It occurred at point 1, and here's the value for that. All right, so next we have for part B is asking how much work was done by or on the gas from A to B, from B to C. All right, now from A to B, uh, we can recognize that process. We can recognize that's just nothing but isochoric process. Okay, so then since the volume doesn't change, I can say then work done going from A to B, right? AB is equals to just 0 because no work is done. Okay, now going from B to C, what type of process is that? Is it adiabatic? No. Is it isochoric? No. Is it any of the ones that we know, isothermal? No. This is something that, just none of those 4 processes that we are familiar with. So then how do we find the work done? Well, we can find the work done by just looking at the, area under the graph. Okay, so we can just find the area under the graph and, get the work done from there. All right, so what we do here, we can say the work done is equals to 1/2, then 0.5 ATM plus 0.3 ATM, then times changing volume, because basically we're doing in terms of, so if we kind of break it down, let me use a different color, right? So we break it down, so we kind of get like this. So there's a triangle and like a rectangle here. So it's 0.5 ATM plus, zero point 0.3, so 0.3 ATM, and 10 6 liters minus 2 liters, which is our change in volume. Okay, then the work done is equals to, so 1.6 liters times ATM, then 1 times 10 to the negative 3 cubic meters per liter, and times 1.013 times 10 to the 5 Pascal per ATM. So converting everything into the uh, units that we want to use, right? Because we had liters and we had ATMs. By converting now everything into, let's say we got 16 liters times ATM from the calculation above, then convert liters into cubic meters and ATM into Pascal, then we can work done as 162 joules. Okay, so that's basically the amount of energy, amount of total work done going from A, B, and C. All right, so then part C is then asking, if 215 joules of heat was put into the gas during ABC, how many of those joules went into internal energy? Well, change in U is equal to then Q minus work done. So if we had 215 joules as Q added, right, heat added, right, and then 162 joules of work done, so minus 162 joules, then delta U then is 50, then 3 joules. That means we have a net gain of 53 joules that increased the thermal energy or internal energy, which means that the temperature will also increase for our system. All right, so that concludes this chapter.